or initial velocity. Slope, yeah.
I didn't take physics for a reason.
We're thinking of variables or parameters. Time. Yeah, and speed was a good one too. A lot of it, basically everything physicists do, like at least like gen physics or like your early physics stuff, is initial velocity and a time, right? Like you can roll something down a hill. How the heck do you have any idea where it's at if you don't know how long it's been rolling down the hill, right? So that's where we're kind of going with that. There's going to be a lot of words. You don't need to write down all the words. I will tell you to write down the important stuff, but try and follow along with me because the idea is important. Otherwise, when you're doing the homework and stuff, you might be able to plug it in, but you're just gonna be so confused on why or what's happening. So the relative positions of objects in motion are dependent upon their velocities at a given moment in time and their starting positions where they start, right? And then we have vector equations and parametric equations that allow us to model movement. So we're starting with just objects traveling in a straight line, right? And we could use that. We could use vectors to help us describe that. So here's where all of the writing comes in, and I mostly just have the writing up there so that I don't forget something. So imagine a line going through points P1, I don't know, maybe there, we could say this is P1, X1, Y1, and I don't know, P2, maybe down here, X2, that's what, I'm not going to write it, I'm going to fix that. That's P2, can I squeeze it in here, X2, Y2, that's a little better, right? So we just made this line off of 2 points. We're just leaving them like kind of whatever, whatever numbers go in for X1, Y1, X2, Y2. And we're imagining it's parallel to some vector A. So this can be A, this little guy here, right? I try my best to make them parallel. They might be a little off. And so that means that this P1, P2 is some scalar multiple of A, right? It's either just bigger or shorter, right? So if we just take this vector and multiply it by something, we should get the distance of P1, P2. And so that's all this says, is to get the vector P1, P2, multiply this vector A by something. We don't know what, but we're going to call it T. What do you think that T stands for in the future? Probably time. And so this is the vector equation of a line, and A is called the direction vector, and T is called a parameter, parametric equations parameter. This is where we want to write stuff down. I'd really focus on writing like the vector equation of a line, like that little thing, and then maybe both of these, right? And this is why I wanted to do all that previous stuff, so we know why it is what it is. A line through P1, X1, parallel to this vector, so something we just made, is defined by the set of points P1, P2, such that P1, P2 is TA. That's everything we just did. So the difference in the x is x2 minus x1, y2 minus y1. That's basically this distance here, right? How far did you, this says how far did you go on the x, how far did you go on the y, is equal to something times original vector, right? That's some scalar multiple of this. So as long as we multiply it by whatever, then we're good to go. And that's how we write a vector equation of a line. Now, a lot of the times, especially in your homework, if the line goes through a point P1, X1, Y1, it won't necessarily give you a P2 because we want to focus on what the actual equation of the line is. right? Because like when you're graphing a normal line, you're not asked to just give me 2 points on a line, right? You have y and x in there. And so when you generalize it, and I don't put a P2, X2, Y2, but I just say, hey, this point's on the line and it's parallel to some vector. What's the equation? Well, it has to go through that point. And then you think of a line, like, right, it's not like this is the only other point on the line, right? You could pick any of these points. And so if you make it general, right, so maybe if P2, instead of being a specific value, X2, Y2, if it was just XY, right, literally like any value on that line, then you basically just get this, right? You replace X2 and Y2 with just X and Y. So like when you plug it back in, you just plug in this point into both of those and you leave the X and Y. So, for anyone confused conceptually, all this lead up and what this is just another way to write a line, right? It's like slope-intercept form, except more complicated. More useful in real life sometimes. A little higher order stuff. And it's called the vector equation of a line because it's in vectors. Okay. I think I'm gonna hit next. Is that okay? I see some pens still going. Okay. Okay. No worries. We're all just waiting on Skylar and Mason. Everybody stare at them and make them uncomfortable.
I'm ready.
Good. Okay. Go. Example 1, write a vector equation describing a line passing through P1, 1, 4 and parallel to A, 3, negative 2. And this is what I mean by like the problems are easy, but to understand what you're doing is a different story, right? Our vector equation was all right, so that's x minus x1, y minus y1 equals t. That's it.
Thank you.
My left? Your left? Who's left?
You're left where I need you to be. Oh, look at that.
All right, we just plugged these in for the values.
It's gonna get way. Oh wait, is that it?
That's it.
Oh, okay.
All right. We just, again, it's as simple as like writing the equation to a line, y equals mx plus b, something like that, right? It's just now it's in vectors because we can. And it's sometimes nice because a lot of times in real life, time is involved. More writing. Don't write it all down. Just relax. Again, I just want to make sure I didn't miss anything. But it's the explanation that's important. So in a vector equation, like the one we just had, that can be used to describe the coordinates for a point on a line for any value of t, which we often call time. For example, when t equals 4, maybe it's 4 seconds. You can write the equation. So this is what we just had. This is what we just had, except now, in place of t, We put 4. So at time 4, or whatever parameter you have, usually time, you just stick 4 in there. And then 4 times 3, negative 2, gives us that vector. And then, right, if we have this vector equals this vector, well then x minus 1 better equal 12, or x equals 13. And we have y minus 4 has to equal negative 8, right, if those vectors are the same. So then y equals negative 4. And so then we get a ordered pair 13, negative 4, which often would refer to like an object's position, right? Like you've done graphing as just graphing, but a graph can describe real life. Remember when I said Guilford is the origin? You can make the world your graph. So like when you say the order pair 13, negative 4, it just depends, like we could say that's a position and it just kind of depends on what you're talking about. Right. Yeah. Just from this previous. Yeah. And so this idea here is how we can split it up into parametric equations, not vector equations, essentially where you have x and y as their own things defined in terms of t. And so this is probably what we want to get down. Parametric equations. But it's the same thing we're dealing with specifically for a line. If it goes through a point, x1, y1, parallel to that vector, then you get these. And that's just coming straight from what we did here, right? If we had t equals whatever, distribute the t, solve for x and y. That's where these came from. So, all right, just took this, made it general, right? If that's normally t, you distribute the t, a1, a2, and then add your x1 and y1 over. That's where those come from. And so you'll notice this weird thing is kind of going on where we're describing a line, right? A line usually has like 2 variables, but we have 3, right? Because we're being dependent upon time, or whatever you choose t to be, which is usually time. We'll get through one more example today. Find the parametric equations for a line parallel to q equals 6, negative 3, and passing to the point negative 2, negative 4. Then make it a table of values and graph a line. Well, then we have that x equals
All right there, okay. Where I know I'm doing. No.
So we're just plugging stuff in. X1 is negative 2 plus t times a1. A1 is 6. I would rather write it as 6t rather than t6. We okay with that? And then we get y equals negative 4 minus 3t. Shut up, computer. It could have been.
I doubt it.
And that's exactly how I respond every time
Yeah.
in my head.
I'm supposed to be doing.
those are the equations. And then it says make a table of values and graph it.
Yeah, when you get like stupid hard, it'll happen. At some point, it'll happen.
So this is where we find out why everything is dependent on time. They tell you to make a table and graph it because I think that illustrates that what we're doing now is really dependent on t instead of, you know, x and y just being their own thing, right? So if t is, I don't know, -1, then we're going to get -2 minus 6 or -8. And then for y, we would get -1, right? -4 plus 3. If t was, I don't know, 0, that makes it easy. Then we get x is -2 and y is -4. Maybe I'll make one little extra row here. I'm picking numbers for t, and I'm finding out what x and y are after I plug t in. Yeah, but it's weird now because we're used to lines being just x and y, but now we have what they're really dependent on is the time. I don't know, if t is 1, then x is 4. Right, and if t is 2, right? You can keep doing this forever. These are just all the points on the line, dependent on t. So at time -1, or at time 0, aka starting position, time 1, 2, so on and so on, you get an object's position on a graph, which again, you can make the world your graph. You can make anything a graph you want. And then it says graph it. We're good with graphing points, right? Like, do I really need to, like, -8, -1, right? It's going to be like here, -2, -4. Alright, there's a line going that way. Just graphing it after.